Hi everyone, this is Abhishek. In this video, I'm presenting you geometric transformations. What are geometric transformations? Operations that are applied to a geometric description of an object to change its position, orientation, or size are called geometric transformations. Sometimes geometric transformation operations are also referred to as modeling transformations. What is the difference between these two? Modeling transformations are used to construct a scene or to give the hierarchical description of a complex object that is composed of different parts. Geometric transformations describe how objects might move around in a scene during an animation sequence or simply to view them from another angle. 2D transformations. Generally, transformation means changing some graphics into something else by applying rules. We can have various types of transformations such as translation, scaling up or down, rotation, shearing, and so on. When a transformation takes place on a 2D plane, it is called 2D transformation. Various transformation functions are applied on an object in order to change the position, size, or orientation of the object. We use three techniques: translation, scaling, and rotation for changing the position, size, and orientation of the object respectively. Translation. A translation moves an object to a different position on the screen. You can translate a point in 2D by adding translation coordinate tx, ty to the original coordinate x, y to get the new coordinate x dash and y dash. From the figure given above, we can find the new coordinates x dash and y dash by adding the coordinates of the original point and the translation coordinate. The translation coordinate pair is called translation vector or shift vector. The above equations can be represented using column vectors as given below. We can write it as p dash is equal to p plus t, where p dash is the new coordinate, p is the original coordinate, and t is the translation coordinate. Rotation. In rotation, we rotate the object at a particular angle theta from its origin. From the following figure, we can see that the point x, y is located at an angle psi from the horizontal x coordinate, with the distance r from the origin. Let us suppose you want to rotate it at an angle theta. After rotation to a new location, you will get a new point p dash. Using standard trigonometric original coordinate of the point px, y can be represented as x is equal to r cos phi and y is equal to r sin phi. The rotation angle can be positive or negative. For the positive angle, we can use the above rotation matrix. However, for the negative rotation angle, the matrix will change as below. Rotation about an arbitrary point. Transformation equation for the rotation of a point about any specific rotation point position xr and yr. As we can see in the figure that the original point, the starting point x, y is rotated about xr and yr, which is denoted in the blue dot, to the new coordinate x dash and y dash. And the rotation angle, as the rotation angle is theta, the equations we use for this rotation are given here. Rotations are rigid body transformations that move objects without deformation. Scaling. To change the size of an object, scaling transformation is used. In scaling process, you either expand or compress the dimension of the object. Scaling can be achieved by multiplying the original coordinates of the object with the scaling factor to get the desired result. Let us assume that the original coordinates x, y and the scaling factors are sx and sy, and the produced coordinates are x dash and y dash. This can be mathematically represented as shown below. In matrix format, you can write it as x dash y dash is equal to sx0, 0 sy, a two-dimensional matrix, into x and y. And as the equation is given below, p dash is the new coordinates of the point, s is a scaling factor, which is multiplied by the original coordinate P. Scaling by a fixed point. The coordinates of the fixed point xf, yf are often chosen at some object position, such as its centroid. Objects are now resized by scaling the distance between the object points and the fixed point. These are the equations used for scaling the point x, y about the point xf and yf with the scaling factor sx and sy. As the equations denote, x dash is the new x coordinate is equal to x into sx plus xf into 1 minus sx. And similarly, y dash is equal to y into sy plus yf into 1 minus sy, where the identity terms xf into 1 minus sx and yf into 1 minus sy are constants for all the points of the object. Homogeneous coordinates. Many graphical applications involve sequence of geometric transformations. An animation might require an object to be translated and rotated at each increment of the motion. The viewing transformations involve sequence of translation and rotation to take us from the original scene specification to the display on the output device. P dash is equal to m1 into p plus m2. This equation is described below. The matrix M1 is a two-dimensional array containing multiplication factors, and matrix M2 is a two-dimensional element column matrix containing translational terms. Multiplicative and translation terms can be combined into a single matrix if we expand the representations to 3 by 3. Three-element representation xh, yh, h called homogeneous coordinates, where homogeneous parameter h is non-zero value such that x is equal to xh by h and y is equal to yh by h. These are the two-dimensional translation, rotation, and scaling matrices. Inverse transformations. When a point is translated, rotated, or scaled, it can also be brought back using these inverse transforms. Inverse translation matrix. 2D composite transformations. Forming products of transformation matrices is often referred to as concatenation or composition of matrices. We do pre-multiply the column matrix by matrix representing any transformation sequence. Since many positions in the scene are typically transformed by same sequence, it is more efficient to first multiply the transformation matrix to form a single composite matrix. 2D composite translation. If two successive translation vectors t1x, t1y, and t2x, t2y are applied to a 2D coordinates position P, the final transformed location P dash is. The composite transformation matrix for the sequence of translation is given below. 2D composite rotation. Two successive rotations applied to a point P. We just multiply the rotation r of θ1 with P and then with r of θ2 to get a new point P dash. As we can see that r of θ2 into θ1, θ2 into r of θ1 is same as r of θ1 plus θ2. The composition equation. P dash, the new point, is equal to r of θ1 plus θ2 into P. Composite scaling. For successive scaling operations, 2D produces the following composite scaling matrix. From the matrices given below, S2x and S2y, matrices comprising of S2x and S2y is the second scaling factor, and S1x and S1y is the first scaling factor. Multiplication of those two is giving us the composite scaling matrix. Computational efficiency. A given equation, as we can see, it requires 9 multiplications and 6 additions. These can be reduced. Actually, only 4 multiplications and 4 additions can be taken place. Once matrix is concatenated, it is maximum number of computations required. Without concatenation, individual transformations would be applied one at a time, and number of time calculations could be significantly increased. Rotation calculations require trigonometric evaluations and several multiplications. Computational efficiency can become an important consideration in rotation transformations. For small enough angles, less than 10 degrees, cos theta is approximately 1, and sin theta value very close to the value of theta in radians. As you can see from the below matrix multiplication equations, x dash and y dash are the new x coordinates, x and y are the x coordinates, original x coordinates, theta is the angle in which it is rotated. Composite transformations often involve inverse matrices. Operations are much simpler than direct inverse matrix calculations. Inverse translation matrix is obtained by changing the signs of the translation additions. Inverse rotation matrix is obtained by performing matrix transpose. Rigid body transformation. Any transformation as translation of or rotation of a set of points such that the distance between the points is preserved, then it is called rigid body motion. In the above matrix, the upper left 2 by 2 submatrix is an orthogonal matrix. The two vectors Rxx, Rxy and Ryx and Ryy form an orthogonal set of unit vectors. The set of vectors is also referred to as orthonormal vector set. Each of those vectors has unit length. Their dot product is 0, as described in the side equation. If these unit vectors are transformed by rotation submatrix, then here is the example described below. T is the translation, R is the rotation. When are done simultaneously, one after the other, then the composite matrix would be as given. Reflection. Reflection about the line y equal to 0 is accomplished with the transformation matrix as given below. A reflection about the line x is equal to 0, which is the y-axis, flips the x coordinates while keeping the y coordinates the same, as shown in the figure given below. Reflection related to the coordinate origin. The matrix used for reflecting the 2D object over the related to the coordinate origin. The reflection axis as a diagonal line y equal to x. We use the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1 for obtaining an object, a reflection of an object over the line y equal to x. Shear transformation. Transformation that distorts the shape of the object is called shear transformation. The transformed shape appears as if the object were composed of several layers that had been caused to slide over each of them. An x direction shear relative to x-axis. This is the matrix used for shear transformation. We can use the equations given below for shear transformation related to x-axis. X direction shears related to other reference lines. We can use the reference line y equal to y reference. By using that x direction shear, we use the given equations. X dash is a new coordinate is equal to x plus shx into y minus y reference, and y dash will be the same. Y direction shear relative to the line y x is equal to x reference, as shown in the figure given below. We use the equations given for shear relative to the line y x is equal to x reference. Raster methods. All bit settings in rectangular area shown are copied as a block into another part of the frame buffer. As you can see, all the points of the 2D object are copied into different frame. Rotate a two-dimensional object or pattern 90 degrees counterclockwise by reversing the pixel values in each row of the array, then interchanging the rows and columns. The given given is the matrix A. When modified by reversing the pixel values in each row of the array, and B is transformed to C by interchanging the rows and columns, where C is the two-dimensional object obtained by rotating the object A 90 degrees in counterclockwise direction. For array rotations that are not multiples of 90 degrees, we need to do some extra processing. Similar methods to scale a block of pixels. Transformation between coordinate systems. Computer graphic applications involve coordinate systems from one reference frame to another during the various stages of scene processing. To transform object descriptions from xy coordinate to x dash y dash coordinate. Translate so that the origin x naught comma y naught of the x dash y dash system is moved to the origin 0 comma 0 of the xy system. Rotate the x dash axis onto the x axis. As you can see from the figure given below, the point x naught comma y naught, which is the origin of the system x dash y dash system, is translated or moved to the point 0 comma 0, which is the origin of the xy system, and then the x dash axis is rotated onto x axis. Alternative method could be specify a vector v that indicates the direction for positive y dash axis. Obtain the unit vector u along x dash axis by applying a 90 degrees clockwise rotation to a vector v. Rotation matrix could be described as elements of a set of orthogonal vectors. From the equations given below, v is the specified vector in the direction of positive y dash axis. V equal to capital V divided by modulus of v, which is vx comma vy. Small u is the unit vector in the direction of x dash axis, which is perpendicular to y dash axis. Can be given by vy comma minus vx, which is also equivalent to ux comma uy. 3D transformation. In 2D system, we use only two coordinates x and y, but in 3D, an extra coordinate z is added. 3D graphic techniques and their application are fundamental to entertainment, games, and computer-aided design industries. It is continuing the area of research in scientific visualization. Furthermore, 3D graphic components are now a part of almost every personal computer, and although traditionally intended for graphic intense software such as games, they are also increasingly being used by other applications. There are three techniques in 3D transformations: translation, scaling, and rotation. 3D translation. In 3D translation, we transfer the z coordinate and x and y coordinates. The process of translation in 3D is similar to 2D translation. A translation moves an object into a different position on the screen. The following figure shows the effect of translation. The figure P is moved to P dash by using a translation factor of t. A point can be translated in 3D by adding translation coordinate x, tx, ty, tz to the original coordinate x, y, z to get the new coordinate x dash, y dash, and z dash. T is the translation matrix described below. The equation we use for translation is p dash is equal to p into t. 3D rotation. 3D rotation is not same as 2D rotation. In 3D rotation, we have to specify the angle of rotation along the x-axis, along the axis of rotation. We can perform 3D rotation about x, y, and z axis. These are represented in the matrix form as given below. Rx of theta, Ry of theta, and Rz of theta are the three matrices that we use to perform the 3D rotation x, y, and z axis respectively. The following are the figures in which it describes the rotation about x, y, and z axis. 3D scaling. You can change the size of an object using scaling transformation. In scaling process, you either expand or compress the dimensions of the object. Scaling can be achieved by multiplying the original coordinates of the object with scaling factor to get a desired result. The following figure shows the effect of 3D scaling. In 3D scaling operation, three coordinates are used. Let us assume the original coordinates x, y, z. The scaling factors are sx, s, sy, sz respectively, and the produced coordinates are x dash, y dash, and z dash. This can be mathematically represented as shown below. Given matrix x dash, y dash, z dash 1 is equal to the multiplication of x, y, z 1, which is multiplied with a 4 by 4 scaling matrix. To obtain the result, x into sx, y into sy, z into sz, and 1. Rotation about an arbitrary axis. Rotation about an axis not parallel to one of the coordinate axes. It requires 5 steps. Translate the object so that the rotation axis passes through the coordinate origin. Rotate the object so that the axis of rotation coincides with one of the coordinate axes. Perform the specified rotation about the selected coordinate axis. Apply the inverse rotation to bring the rotation axis back to its original orientation. Apply the inverse translation to bring the rotation back to its original spatial position. Initially, the first diagram describes the initial position. By translating the object to the origin, which is described in the diagram 2, in step 2, we rotate the object along the axis. In step 3, we rotate the object around the axis. In step 4, rotate the object back to the original axis. In step 5, we translate the rotation axis to the original position. This is the equation given for the components of the rotation axis vector. V is P2 minus P1, which is the unit vector, which is the vector in the direction of the rotation axis. To get the unit vector U, we divide the vector V by its magnitude. Quaternion methods. This is an efficient method. This requires less storage space than 4x4 matrix. This method is important in animations which often require complicated motion sequences and motion interpolations between two given positions of an object. Scaling with respect to an arbitrary point. To scale about an arbitrary point P, px, py, pz by sx, sy, sz. First step is translate the object by t, which is minus px, minus py, minus pz. So p coincides with the origin. Scale the object by sx, sy, sz. Translate the object back to px, py, pz. This is given below is a matrix representation of the above description. Reflection with respect to principal planes. 3D reflection can be performed related to a selected reflection axis or with respect to selected reflection plane. The 3D reflection matrices are set up similarly to those of 2D. In 2D, reflection with respect to axis is equivalent to 180 degree rotations about axis in 3D space, whereas 3D reflections with respect to axis with respect to a plane are equivalent to 180 degree rotation in 4D space. Given below are the reflections related to xy, xz, and yz plane respectively. Transformation between 3D coordinate axes. An x dash, y dash, z dash system is defined with respect to an xyz system. To transfer the xyz coordinate description to the x dash, y dash, z dash system, translation that brings x dash, y dash, z dash coordinate origin to the xyz origin. A sequence of rotations that align the corresponding coordinate axis. Scaling transformation may also be necessary. These are the differences. Thank you.